Um, Hello, everyone. My name is Catherine. I'm a PhD student with David Rolnick at Mila and McGill in Montreal. And I'm here to present our recent paper, which was recently published at AAAI 2026, and is called BATIS, Bayesian Approaches for Targeted Improvement of Species Distribution Model. BATIS is the acronym of our approach, but is also the name of a cute bird species that can be found alongside the coast of Eastern Africa. And you can see Abatis on that slide. And we used birds in our papers, so that was the inspiration for the acronym. So this slide, I'm guessing everyone here in this crowd knows what species distribution models are. So I'm just gonna quickly skip that slide. But among the larger family of species distribution models, there are various biological quantities we might be interested in estimating. And for this paper specifically, we were mostly interested in predicting what we call encounter rates. So encounter rates can be estimated from a data set of presence-absence data, in which people collect what we call in our contribution checklist-based surveys, which are simply binary vectors where you will have a 0 if the person hasn't observed the species and a 1 if the person has observed the species. And from those checklists, you can then estimate the average rate at which observers encounter species at a given location. And it is a standard assumption to assume that this estimation converges to the true encounter rate with the more checklists you collect. So in areas where you have tons of observation, the encounter rate estimate you get will be much better than the ones you might estimate in areas where you might only have 5 checklists, for example. And the encounter rate is also a little bit different than the occupancy probability, for example, because it also depends on how observable a species is. So it can be viewed a little bit as a product of both occupancy and observation. And with any kind of SDMs, as we know, learning with spatially heterogeneous data set is super hard. And the effectiveness of deep learning-based SDMs and SDMs in general is ultimately hindered by the abundance and geographical coverage of the data used to train them. So we have seen in recent years nice progress that was done by leveraging super large data sets such as INAT or eBird. But these data sets tend to have super striking geographical biases, such as this in this example on the right with Kenya, where we see that the darker green the patch is, the more visits there was to that cell. And the areas where people tend to mostly sample data tend to be mostly around closer to roads, densely populated cities, or places that are popular for tourists, for example. So this is a big challenge when we try to learn relevant biological signal from this kind of data. And we might be tempted at first to pitch all the data we have within a larger learning model and try to learn relevant biological information from it. But the biological information you get is not equal across all locations in your data set. And if you were to include all the data, both on super well sampled areas and very remote areas as well, you will end up having tons of locations with super noisy labels. And it's very challenging to balance between these noisy labels and the more informative information you get in densely sampled areas. So the motivation of our papers was trying to find better ways of leveraging the little information we have in remote and undersampled areas, such as the areas highlighted in red on the right of this example. So to tackle this issue, we introduced BATIS, which is a framework for iteratively refining the prior prediction of an SDM with the help of limited additional underground information. So what we did is that we looked at the distribution of all of the data set we have access to, and we put aside the areas that didn't have enough observation to be included in the training data set. And we formulated the assumption that species observation were following a binomial distribution parameterized by the encounter rate. And this allowed us to formulate a Bayesian inference problem in which we can put a beta prior over the encounter rate. And because the beta is the conjugate of the binomial likelihood, the posterior is also a beta distribution. And that gives us an updating pipeline that is closed form and very easy to compute. And with that updating pipeline, we were able to first train a machine learning model that is trained on mostly sufficiently sampled areas, and then use the very limited information within a Bayesian pipeline to try to improve this prior prediction. So BATIS leverages uncertainty-aware approaches to estimate for each data scarce location both the mean encounter rate and its associated variance. We use these outputs to parameterize the beta prior that we see on that slide. And the beta prior depends on two parameters, so the alpha and the beta parameters. And these two parameters are each depending on the same two variables as well, which is the mean encounter rate and the variance of that encounter rate. And we used deep learning models that can also estimate the uncertainty associated with an estimate. So we sampled models from the uncertainty estimation literature in machine learning. These uncertainty estimation approaches work quite differently than what you can usually see in statistical ecology, for example. It's really not most of the time based on MCMC estimation, for example, because deep learning models are so large that it's not really possible to do so. So it's much more heuristic based, if I can call it like that, but there's still proofs that can tell you how much these estimates can get to the true uncertainty estimate that you would ideally want to estimate, but can't due to the size of these neural network model. So to summarize, BATIS works by taking for each data scarce location a prior that is generated from a DeepSDM model. And then with the few observation you have, let's say 5 or 10 checklists at that location, we combine the prior from the deep learning model with the additional observation to get an updated posterior predictive predictions. And the more observation that we collect in these locations, the better ideally the model gets to predict species distribution at that location. To test our approach, we built a benchmark data set that was mostly inspired by what was previously done in the Sabvert paper, which was done by my colleague, Belly. And we created a benchmark data set from that data that mirrors the real-world scenarios in which BATIS can be applied. So, for example, in the USA, because there's a lot of areas that are super well simpled, we simulated a situation in which those areas had much less, far fewer checklists to compute a proper estimate on, and we validated that our approach could get closer to the true estimate that we could estimate from the whole data set of the USA. We also included eBird observation from Kenya, which are much more sparser, and also South Africa, which is also a great example of of large spatial biases in citizen science dataset. We benchmarked BATIS across a wide array of deep learning approaches that can estimate uncertainty. We included both approaches that can estimate just epistemic, so model inherent uncertainty, and also aleatoric, so what we call data inherent uncertainty as well, and also models that can try to estimate both of them at the same time. And we compared these uncertainty-aware neural network approaches to both non-uncertainty-aware deep SDMs and statistical ecology baselines as well. And what we got was that approaches that can estimate both aleatoric and uncertainty estimates at the same time, such as the heteroscedastic regression neural network, for example, perform far better than approaches that strictly focus on epistemic uncertainty, which are represented by all these graph lines that have a stagnated performance and don't necessarily improve much as you get more and more checklists, while in comparison, by trying to estimate both aleatoric and epistemic uncertainty, we were able to get a model that was able to significantly improve its prediction with very few checklists. We also looked at the iterative improvements we could get by species. So these are 3 examples of birds that can be found across Kenya, and the more checklists we add to the model, the better we get at estimating the overall distribution in the test data set, and we can get pretty great encounter rate estimate with as few as 5 checklists using that approach. So to summarize, our approach is able to combine broader ecological patterns that you learn from an overall machine learning model that learns large-scale patterns, and then combines it with fine-grained insight that you can get from an uncertainty-aware pipeline. And the more uncertain the estimate is, the more the fine-grained observation will matter in the final prediction, and the less uncertain the model is, the less these fewer observations will matter in the posterior predictions. Our approach is able to improve SDM prediction from limited and noisy additional data in remote locations, and is also able to leverage uncertainty, like I said, to highlight the relevance of local environmental factors when it does matter or not. But what BATIS cannot do, however, is that it struggles to improve SDM prediction at location with no additional observation. So if you don't have, it doesn't propagate updates across location. It's very much location-based. And it's one of its main limitation. And it cannot also perform well without a good uncertainty estimation algorithm. In our case, we picked approaches from the uncertainty estimation literature in machine learning, but we didn't propose anything new in that regard. And these approaches are never perfect. So it's one of the main limitations of BATIS as well. And it also struggles to transfer fine-grained insight to similar location. It was not, this is much more of a stepping stone, and a next step will be to make it able to do so. So to conclude, BATIS can rapidly improve SDM prediction in data scarce location by combining broader ecological patterns with fine-grained location-specific insights. Our results suggest that machine learning approaches focusing on aleatoric uncertainty provide a better measure of observational variability than those focusing on epistemic uncertainty for that problem. And further works on our side will be to extend BATIS to for example, an active learning framework that could help guide data sampling from those uncertainty estimates, adapt it in order for it to be able to work on presence-only datasets, which we're currently working on, and also work on the time dependency and additional bias control. more than just spatial biases. So thanks to my co-authors, which include among this group David and Millie, which are part among us for this event. Thank you.
Thanks for the talk. I have a kind of side question, more about the applications that your approach could have. There's something that we didn't discuss much this morning until now with SDMs, is the fact that when you fit SDMs to a region or national or a country, you could miss a lot of ecological conditions that a species can stand. And that becomes a huge problem if you predict in the future, because you might miss part of the, for instance, the climatic niche of the species. So it's called niche truncation issues. And we propose the nested SDMs to try to prevent that. So it's the idea to have a hierarchical model where you have a global model that fits the entire conditions of the species, and to combine it with finer grain data.
Yeah, that was the inspiration.
And actually, my question is, could you expand your model to also account for this issue and to try to really also fix this niche truncation issue with your approach? Because you mentioned several times that it has the advantage that you can combine large extent information with finer local information.
If we were to extend the approach to be able to propagate the uncertainty to similar areas, I think that could help fixing that issues, because what we were able to show with that approach is that, yes, if you have like 4 or 5 observation, you can get much better estimates by combining it within an offline Bayesian pipeline like ours. But in cases where you have no observation at all, then the approach is useless. But it can still gives you. I'm not sure if I understood well your question or if my answer is the proper answer. But yeah, I think by being able to propagate the uncertainty and the estimates across locations that are similar, we could.
But it's not only the uncertainty. With this nested approach, you have different ways to combine the large extent with the small extent model. One is the covariates, to use the predictions from the global model as a predictor in the local model. But another way would be to really try to use a Bayesian approach. And we tried that, but it's very slow and it's very difficult to implement for large scales. So I was wondering whether maybe you are also but it's focused on uncertainty. But I mean,
it's definitely a different way of doing a Bayesian approach in our case. Just the idea of using a deep learning model as the prior already breaks what is usually being done in Bayesian ecology model. But yes, maybe the uncertainty estimation approaches in deep learning could help for those models. That's a good thing to think about. Thank you.
Hi, thanks for the great talk. I was wondering, so if you have a lot of locations with just a few data points, and you can use the data points for inference, how do you go about validating the model at those locations if you need those data points to do the estimates? And especially if that's, how that's related to maybe local observer bias, for example.
So if I understand your question correctly, you're asking what are we including the sparsely sample location in training or not? Is that?
I guess it means when you test the model, you need to use the observations at the test location, right? So, so I was wondering how you...
Oh, we did it. Basically, the data set which we trained the model and tested on is like a simulation based on the real. For example, if you take the data set from the United States, if you take the true data set, it's really not a good application for that problem, because most of the areas in the US are quite well sampled, especially if you compare it to other countries. But we can use that benchmark data set to then simulate cases and remove data, for example, which the model will not see. But then in the evaluation pipeline, we're able to benchmark it against the true value that the model doesn't necessarily have access to. Does that answer your question?
Yes, thank you.
Yes.
So if you're simulating in that way, how much variation do you get in your predictions depending on which subset of the predictions you use that's like the initialization?
Like the subset of, because the only subsets we consider is that basically we picked a random subset of areas that had a lot. Like basically what we did is that we separated the data set between super well simple and super sparsely simple. And from this, and we built a training data set that took a random sample of both the super well simple and the sparsely simple. But across the various random samples we tried, the results were quite consistent.
So I'm not talking about the sampling of the areas, but actually I guess you were saying you could synthesize, if you have an area that has a lot of samples, you can basically get what you're considering an oracle, which is what happens if you fit the model using all those samples, right? So now you're synthesizing actually only observing a subset of the checklists, or maybe I'm misunderstanding.
No, we would, exactly. We would consider a subset of the super well sample areas, and we will remove all of the others to try to simulate, we want to apply BATIS to those locations specifically. And then at test time, we have the true value we compute from, the oracle, like you said.
So I was asking if you did any, what if you do different random subsets across the super well sampled? Mm-hmm. Do you get a lot of variance in your model? Like so say you have 100 checklists in an area, and now you're picking n equals 3. Mm-hmm. Did you try a bunch of different random samples of n equals 3? How much variance is there in the outputs when you synthesize getting different initial checklists?
How much the variance varies depending on the subset you use?
I know.
Sorry.
That's the question.
I'm not sure, but I think we did partially what you suggested. And what I can surely say, if I understood your question correctly, is that the variance was consistent across various samples, but we didn't investigated how much, where did the variance specifically change depending of the subset we took, which definitely can have an impact on some areas. Will have much more variances because in that random subset, there was more but on average, the average prediction, at least with the metrics we included in the paper, didn't necessarily change much across random samples. Sorry.
No, it's good.
Yeah,
we have time for one more question.
Also, I think that the variance becomes smaller as when you increase the number of samples in that you use as train. So bigger is the training sample, with the subset that you take, smaller is gonna be the variance, and less variance you're gonna have between different sampled area, I guess.
Yeah.
So it's just a matter of the sample that you consider and the size of it, I guess.
Yeah, no, exactly. And the ideal case will be to have as much data as you want to have very little variance, but we simulated different cases where we knew the variance was going to be potentially higher to test does BATIS works when the variance is super high, and how does the performance change in different cases with different levels of variances across the data set.
Did you have a question?
Yeah, maybe.
Is it a quick question?
Yeah, sure. Basically, the data that you make is site specific, right? Location specific. Have you thought about benefiting other location by?
Yeah. Thinking about that.
Okay.
The straightforward way of doing this would be to have some sort of kernel based, propagating updates. But we're also thinking about potentially some other variational approaches that could help propagating updates and make it much less location specific. But it's a stepping stone towards that, I may say.
Interesting.
Okay. Thank you so much, Caitlin.